Hello, this is Mark Summers from Summers Technical Services. This is our third of three videos to help with the bridge optimization design project. So we're going to be in SOLIDWORKS. We'll be running SOLIDWORKS simulation, doing a static analysis of our beam. So let's go see what that looks like. So first thing you're going to want to do in SOLIDWORKS is make sure you've got your simulation module loaded. There's lots of different modules that SOLIDWORKS comes with. Some of them load automatically, some don't. So go to Tools, Add-ins, and make sure that this SOLIDWORKS simulation module is checked on over here. That'll load it now. And this checkbox over here will tell you to load it up every time you start SOLIDWORKS. So check those two checkboxes, and you should get a tab on your with your other tabs up here for these different commands. You'll have one called simulation. So now we're ready to get started. So the first thing you can do is one thing you can do is only command that's not dimmed out is start a new study. So we'll start a new study, and you'll see that there's lots of different options. We can do thermal, fatigue, buckling, lots of different options. We're going to do a static analysis, constant loads. No, loads don't change over time. And we'll call it, I don't know, TSU-078-00-01. And you say OK. So now we've got a new tab down here that represents, it's got a different tree over here because now we're looking at the simulation. If you want to go back to the model, just click the tab down here. That'll take us back to the model. We can make changes as needed. So now we're back over here. Now I've got my commands up here, and I've got my tree like I'm looking for. So now we're going to just answer questions left to right and then run the study. So the first button is apply material. You just hit apply material, and you go through and you'll go define which one you've already created these based on the first video. So I'm going to go in and grab my one I chose, this aluminum here, and we'll say apply close. And you'll see on the tree, there it is. It's assigned, material is assigned there. Next button we're going to skip is the evaluator. We're going to go to Fixture Advisor. We're not going to hit the Fixture Advisor. That pulls up a little wizard that walks you through all the possible fixtures you can do, but I want to just have you use the pull down and go to Fix Geometry. So we need to fix these bottom edges of the beam. This side's going to be a hinge, and the other side's going to be a roller. We're going to use the Fix Geometry option, and we're not going to choose these rollers. I want to manually put these in. So leave it on Fix Geometry. Grab this edge, not the face. Grab the edge, and grab this edge down here. And we're going to go open up these two options down here. We want to open up this symbol setting. Depending on what your graphics card and your monitor display is, these may be kind of small, so I bumped mine up to 200. That just changes the size of the little icon down here. And then I'm going to go to Advanced tab. I'm going to pull that down. And here's where we define the three directions we want to keep it from moving. So there's another box down here. This lets me define a direction so I can define these displacements. So I'm going to click inside this box. This blue box has my two edges I selected a minute ago. So I'll make that blue box active. I'm going to grab this face right here. And this is where I tell it my displacements. I want to have 0 displacement. I want to fix it, change that to inches. The direction perpendicular to that face, that's the Z direction. I don't want it moving in the Z direction. So I click that button right there, and that makes that displacement 0. I don't want it moving up and down because it's on that hinge won't allow it to move up and down, so I'm going to push that button and make that go to 0. And I'm also going to control it in the X direction, moving left to right, because I don't want this thing to roll back and forth, so I'm going to push that button right there. So I'm telling it, do not move in the X or the Y or the Z direction on those two edges. And I say OK. And you can zoom in here and you see these little icons. You can see there's an arrow pointing in the X direction, Y direction, and Z direction. So that means I did that one correctly. So that edge, those two edges are fixed. They can't move. Now I'm going to spin it to the other side and do a similar thing, except this time I'm going to create a roller joint. I'm going to allow it to move in the X direction because it's on those rollers. So again, I go Fixture Advisor. I use the pull down, and say Fix Geometry. I grab these two edges like I did before, put them in that first blue box, and I'm going to come down to this symbol setting. And again, depending on what your display is, you may or may not have to change that. I'll make mine 200. Under Advanced, I'm going to select this box right here so I can define that direction again, like I did a minute ago. Select that box, make it active. I'm going to grab that face. Now I've defined that direction again. And this time, I do not want to constrain it in the Z direction. Here's the XYZ triad down. You can see what I'm talking about, because it's on those rollers. And so I want to change this to inches like I did a minute ago. I'm not going to push this button because I want it to be able to move in the Z direction. I don't want it to move up and down because it's still a hinge over there. So I'm going to, excuse me, a roller. So I'm going to turn on up and down. It can't move up and down. And then I'm going to also, like I did the other one, I want to say it can't move left or right in the X direction. So it's just like before, except I do not select this button here because I do want it to be able to move in the Z direction. So once I say OK there, I can look at these icons, and you can see there's only two directions. It doesn't let it move. It doesn't let it move left or right. It doesn't let it move up and down, which is exactly what I want on my, based on my constraints I gave you. Okay, so we've done that. You can see the little fixtures. This is just like in my model tree, and now I've got simulation items in here. So my references or my fixtures are done. External loads. And so what I want to do now is pull this down and go to force. I want to add a force to this top surface. And so when you calculated your W value, that is pounds per inch along the length of this thing. So the way I want to define it in this simulation is I want to get the entire load, not so many pounds per inch, but a total load. And so that's when I'm going to take my W value, pounds per inch, and then multiply it by 24 inches to get a number for my total load. And so I'm on force. I selected the face. I'm going to change the units to English. Make sure you get English, so I got pound force here. And I'm going to change this number to my W value times 24. Yours will be different depending on what design you use. So now I say OK, and now I've got that load on here. So I've got the material defined, I've got the constraints defined, I've got the loads confined, and now the next thing to do is to mesh it and then run it. And so to do the mesh, what it does, since this is a sheet metal part, it does a 2D mesh, very efficient. So I'm going to use this pull down. I'm not going to hit run this study. I'm going to use the pull down and say create mesh. And there's a slider here. I can slide it to make it a real coarse mesh or a fine mesh. Finer mesh is going to take longer to run, but it's going to give me a better answer. Coarse mesh is going to be not as accurate as the answer, but it'll take less time to run. You might want to leave it in the middle. I've got a powerful CPU and a bunch of graphics memory, so I'm going to run it all the way to fine and say OK, and it calculates the mesh, and it breaks it down into these little triangles to approximate the geometry in this mesh. And so you can see how the mesh looks here. So it's a two-dimensional mesh. It has no thickness, but it knows what the sheet metal part was, how thick it was, and so it's keeping track of all that for us. And this is another reason to do sheet metal designs when you get sheet metal parts, because you have a very efficient mesh here. So now I want to hit the run this study button. This is going to run the analysis for me. So I'm going to run this study and watch it crank up here. And I got a pretty speed. It runs pretty fast. Okay, so now I've got my results out here. We need to ask for two specific results. We need to know the normal stress on the Z face, on the Z plane. That's going to give our maximum, that's going to give our stress that we calculated, that maximum normal stress due to bending is going to be stress on the Z face. So I'm going to right click. This von Mises stress is not what I want. That's not what I had you calculate. This is a different stress that we'll talk about if you take my ENGR 3311 class. So I'm going to right click on stress 1 and say edit definition. I'm going to change the definition of those results. Instead of asking for the von Mises stress, I'm going to tell it to give me Z normal stress. That's what we calculated in the last video. I'm going to change these units to PSI because all my numbers are on pounds and inches in PSI. And that's it. I'm going to say OK. And it's giving me this deformed shape. I don't like that deformed shape. I'm going to turn it off so it goes back like that. So now I can see my maximum and minimum stress. Now what I need to do now is I need to clip this off at the top because I only want to see up to my calculated maximum stress that I did in the hand calculations last time. So the way you change that maximum value is you double click this, and double click the legend there, it's going to pop up and it's going to let me override this top number here. So I'm going to check that checkbox off, and I want to type in my maximum stress that I calculated on the previous page, which in my case is this number. So it just reset the amount of stress that it clips off here. So that's the maximum it's showing. And so this makes sense to me. The stress is highest in the middle and it goes down to 0 on the edge. There's stress on the top, but these top numbers are not, the stress on the top is going to be in compression. And that number is not as big as the tensile stress at the bottom. And that's because that CXX value, remember the distance to the bottom edge was further from the neutral axis. The distance to the bottom edge was bigger than the distance to the top edge. So both of them have stresses, but the maximum values are going to be here at the top, excuse me, at the bottom, which are shown here in red. So once you change that legend, now I'm going to go in here and I want to take a look and make sure that that maximum stress value that I put in at 10,333 in my case, I want to make sure that that is really the maximum stress. And the way I do that, these plot tools, there's lots of different things we can do in these plot tools. I'm going to come down here and do ISO clipping. What I'm going to do is, once I click on ISO clicking, I can drag this slider and I can make it only show me stresses that are below a certain value. So as I start sliding this thing, go way over here, there's lots and lots of stresses bigger than negative 4450. But as I slide this to the right, the model starts not displaying the stresses. You can see the little slider going here. It's going from all negative. So I'm going to slide it all the way over. And I'm going to hope that all these stresses pretty much go away. See how they're going less and less and less? And by the time I get all the way to the top, they're just about all gone. That means that the maximum stress that I'm seeing on my simulation is pretty close to the maximum stress that I did my calculations for. And that's what you want to see when you slide that slider over. It should go to where almost all the stress goes away. If not, then you got a problem with your calculations. We need to talk about it. Okay, so I've convinced myself the stress values look good. Now I'm going to look for the displacement. Excuse me. So I'm going to edit definition. This displacement I'm getting is a resultant displacement. It's a XYZ combined displacement. What I want to do is change the displacement so I just see the Y direction displacement, because that's what that equation, I calculated with that equation, was the Y displacement. So I'm going to come up here, instead of resultant displacement, I want to say give me the Y displacement, because up and down is a Y direction. I'm going to change these units to inches. I'm not sure why they keep going to millimeters. Change that to inches and say OK. So now I'm going to double click it to make it active. Right now the stress is active. I'm going to double click the displacement, and now it's active. And this is the deformed shape again. I'm going to turn that off because it's too confusing to me. And you can see there's displacement here. This top plate doesn't say fix. It deforms itself. And so these displacements are going to be larger than what we calculated. But we'll get a feel for what this would be closer to the real displacement, not based on that calculation. I'm going to turn that deformed result off. And I'm going to come over and look at the numbers. And this number right here, the maximum deflection here in the middle on the top, is right here. That number needs to be less than our requirement, which is L divided by 360. So calculate L divided by 360, compare it to the maximum displacement you have on your design, and as long as the number on the simulation is less than that number, then you meet the requirement. So those numbers you should report as well on your project. So that takes us to the end of the SOLIDWORKS simulation portion. This will get us through part B of the assignment, and then the next part C we'll talk more about in class on Wednesday. So until then, we'll see you in the next video.